So welcome Adil, welcome Shital, and I hope everybody's watching this. So the question that came up from Shital earlier was whether there's R programming skills needed for the midterm exam. And the answer to that is no, there will be calculations involved in the midterm. So there will be calculations involved. There will be interpretation of outputs involved. And please know the theory very well. So it's not the easiest of all exams. So be prepared. Follow along with the lectures and utilize the discussion board, please, to make sure that you understand the material fully. It's as said, it's an intense class. We don't have much time. We have two classes per week, which is quite tough. And this will basically stay at the same frequency. I hope you all have looked at the syllabus in detail. So there's the midterm, and then we're transitioning over to predictive modeling with logistic regression, which is then a multiplicative model. So essentially, it's getting the tenses it's gonna be more complicated on the road. So make sure to keep pace with the class, make sure to resolve all our issues immediately, reach out to me via discussion board. And as for the R coding will really be most important for the research mode. So I will be creating also the coding and the interpretation of these results then in the research node. So you're not expected to write a full research paper, but I'm expecting also some discussion and some review of the data as it was presented and analyzed. So Adil had a question concerning lab 3. So I have here the labs open. So let's go through them one by one. I will be sharing my screen. Hope you can see it now. So, is this time of the day suitable for both of you? So you weren't on last week. So is this a time that works for everybody?
Yes, this is a good time, Professor.
Yeah. So 7 p.m. on a Monday and possibly also on a Wednesday if needed. That works for both of you.
I know it works for me most of the time, but it depends. Are you going to post these recordings on Blackboard or?
Yes, I will post the recordings, but it's important that I have to something to explain, right? So it makes it easier. I don't want to record and repeat the entire lecture. If anything was not clear from the lecture, and I will review all the lectures as we go, because some of the students had some comments on the lectures and there were some aspects they wanted explained in more detail. So I think I want this to be quite interactive if possible. So if you have a question, please loop back to me immediately. I'm going to do my best to guide you to resources or explain it again in a way that is more amenable to you. Okay, I hope that answers the questions for now. So essentially, we have now lab 3. So this is basically just starting the knitted package. And Adil, you had some issues loading the data set, the French mail data. Did these be solved?
Yeah, it was solved. I figured it out. It looks like I wasn't loading the path file originally when I typed it in.
Okay. Okay, no, but I'm glad that you resolved it, and I like the dynamic that is going on the discussion board to help each other. So I think that's wonderful. Okay, great. So this is starting the knitted package, and here essentially we're seeing the first part where we're setting a seed. So again, setting the seed is influencing the randomization of numbers in the respective simulated data frame. So you have R norm, you have R binom and R norm as simulating a normal distribution around the mean following a certain function that is here defined. Professor Zhang has basically quantified this here according to the coefficients discussed in class. So when you use set seed, this basically gives a starting ground. So all of these simulations will then basically result in reproducible simulations. So when we have now age, this will essentially simulate age as a vector. So the outcome, let's clear the environment actually. It's a little bit easier to follow. Okay. So we're setting a seed. We're building age. And when you look at age now, it's essentially that what I said, it's a normal distribution that is following a normal distribution around a mean of 35 with a standard deviation of around 5 and 100 repeated entries. Same with sex. So with sex, you get a binomial distribution following an equal distribution, basically around, it's either 1 or 0, it's 100, and they're basically split in half. So that means there are 50 zeros and 50 ones. So if we do some sex, that should be close to 50. So it follows it with the law of large numbers. The more iterations you will be using, the closer we'll get to 50. So this is a random sample that they have drawn, aiming for a prevalence of 50. So we have now SL, so this is our glucose, same thing. And the SPB is now built, again, 100 individuals, and the mean is modeled based on age, sex, and this serum glucose. So essentially, you take the same function that was developed in class. You're building SPB, and this follows now this normal distribution that was used also in class. So we're seeing now this distribution, seeing some outlier, but it follows a normal distribution around the mean that is defined by this function. So mean SPB gives us a mean that is to be calculated based on the variables here, on the frequency of sex, on age as a continuous variable, and the same glucose as a continuous variable. So age and sex are now considered confounders in the simulation. And the SL is the sugar level. So we're fitting a model that essentially will give us fit 1. So you essentially, when you look at that, you have, oops, sorry. When you look at fit 1, okay, let's zoom in a bit. So you have here fit 1 followed by the pipe, which is equal to the equal sign. So you're packing this model in its entirety in fit 1. So when you would look at fit 1 now and you address it with LS, which gives you a list of all components included in your object, and you go on LS fit 1, you get all these individual aspects shown by R. So essentially, if you go on LS, LS coefficients, you get all these coefficients displayed now. Fit 1 coefficients, sorry. So you get the coefficients out now. So you have here what you see in the summary in its entirety. And we walked through the individual components of summary last time. So you can extract the coefficients alone by using the coefficients term. And LS will always allow you to see what each of these objects contain. So not only can you pack LS fit 1 in an object, you can also pack a summary of fit 1 in an object. Because as you can see, summary of fit 1 gives you even more information. So all of these individual components can be treated as an object and can basically be extracted. And this is what we're doing in the actual lab assignment. We're doing this and extracting coefficients in the iterative loop. So, okay, so summary can be an object, summary fit 1 could be an object, but fit 1 essentially is containing the model in fit 1 as an object. So this is the printout, this is summary fit 1. So now we want to build a design matrix. So this essentially is nothing else but your individual entries shown by the model. So this is pretty much like your fitted values, right? So if you would use this over the entire estimate, so you see here the entries of serum glucose with an intercept of 1. When you include now as an additional confounder, considering that, okay, now here actually we're including age now. Okay, so we're omitting sex because it's being built into the model later on. So this would essentially be the way how you adding an additional variable in there. So you have now serum systolic blood pressure predicted by serum glucose and additionally adjusted for age. So this again follows the same principle. You pack that in fit2, you can call it and analyze it and investigate it now with summary and pack this summary again in an object. Same principle applies. What you get now in addition to that, you get changed and you get changed intercept, you get essentially all else being equal, you basically get the effect of 1 unit increase of serum glucose on systolic blood pressure. So this will be with each unit increase of serum glucose, you have an increase of blood pressure of 1.94. Now you have instances where you need to compute the output of a regression with several functions. So if you want to, and we looked at this before, if you want to explicitly get the coefficient out, you can either do this with fit2 coefficients like I did before, or you can do this with coef. With the coef function, you basically will extract the coefficients, and these are consistent with what we've seen in the summary. With confint, you get the corresponding confidence intervals, and this is a very important function essentially because it allows you to get the confidence intervals out and export them, for example, in a table. An easier way to do that is by using the Stargazer package. And I hope, did you have any problems with installing the Stargazer package?
So far I didn't get up to that step yet, Stargazing.
Okay.
Neither.
So okay. So Stargazer is actually a package that uses kind of produces aesthetically beautiful printouts of your results. So if you run Stargazer, you basically tell Stargazer, okay, you want to look at fit1, which is the one without the age, fit2, which is the model with age. You can customize the table, the main title of your table. You can type any kind of additional options, like you can type it as a text. You give it the default style and you skip the header. So the output of this Stargazer function will be this, where essentially you have an aesthetically more appealing way of depicting your models next to each other. So you have the same information, but it summarizes in a format that you hypothetically could not really. I don't think that many journals will accept this as a format, but you hypothetically, it's nice for reports, for example. If you prepare reports, and I'm flagging this for the research note because that could be a nice way to essentially present your reports then in the research note. So Stargazer is quite a useful package to kind of give a good overview over regression models. So it basically contains the same information as the summary, but it's just it's a nicer way to export it and use it in RMD files and not files. So now we're coming essentially to the loops. Are there any questions so far with the models? I think they're fairly simple at this early stage, right? If no questions, we can carry on. So you remember from last time we have I equals 1 to 3. That gives us a vector that is containing 1, 2, and 3. The length of this vector is going to be 3 because it's 3 entries. And if you want to now create a loop, you have a for loop that runs from 1 to 3. You can hypothetically, you can also 1, 2, 3. It repeats it 3 times. And for each of these entries, it will start with 1. So in the first iteration, it assigns 1 to I. In the second iteration, it assigns 2 to I. And in the third iteration, it assigns 3 to I. And it runs repeatedly through, using always I for each iteration. So here, 1, 2, 3, that gives you these 3 iterations. And that's important because if you want to repeat something over a certain period, a certain amount of times, you can customize this easily here with this for loop. You can, of note, you can replace here if you want to repeat it from 1 to the length of a certain vector. Let's say you have you want to do a certain number of iterations, which corresponds here with the length of age, so which would be 100, right? So it's 100 entries, and you want to repeat this 100 times. You could hypothetically replace this 3 here with length of age. So length of age we know is 100. So then it would basically R would take that value that derives from this coding snippet and would use this as the number of times it repeats a certain loop. So this is the for loop. So this in the simplest form is then really just a few lines. And we have here always after the for loop, it will look for a curly bracket. So with the curly bracket, you're telling the loop, this is where I want you to start. This is where I want you to end. And I want you to do this in between. And you can have whatever you want to display in between or calculate in between. You can basically do here with this loop. So hypothetically, if you want to do, let's do length of age, and we calculate now. Let's do let's display for each individual the blood pressure. Print SPP for I. So now it will show you for each entry, the entry of blood pressure for that individual. So you really can individualize this loop to do whatever you want R to do in an iterative fashion for you. So that's a for loop. Let's not scroll through it. Okay, so now we run this again. That's back to being 3. No. So I just need to customize this to kind of for you to see how powerful such an for function can be. And we're using it then later in the assignment. So allocate and fill. If you want to create a fill vector, you're basically getting here your vector displayed. And you're basically creating a vector. You're creating a numeric vector of the length of 10. It fills it on the first step, it fills it just with 0. So, but now you want to fill it with I plus 1. So if you're adding now with each iteration, don't forget, if you go through fill vector, each I will jump from 1, 2, 3, 4 up until 10, and it will take that respective I it's at, and it will add 1. So if you're running this loop, you get now 2 for I equals 1 plus 1 is 2. And you get this with each step again added. Now you want to replicate something, and you are replicating here a result. So if you inspect your result, you basically get a matrix and you get an array. And if you plot result, what you're basically getting here, you get here 6 replications of a normal distribution where n equals 10. So you have 10 entries, which you can see here. And this creates this matrix for you. It has a mean of 0. It has a standard deviation of 1. So it does nothing else to create 6 independent vectors next to each other, where each of these vectors is built of a sample size of 10 with a mean of 0 and a standard deviation of 1. So each of these basically follow the same pattern. And with replicate, you can basically build such an matrix. So this is just basically setting the stage. So now we're getting to the lab exercise. So use different seeds to see how the result changes, especially the coefficient for SL. So if you want to set seed now, you're setting it to 1. So essentially you want to replicate your fit 1. You want to replicate your fit 1. And you're seeing now a certain coefficient with your fit 1. So you see now, of course we need to replicate it. Build a new simulation. Okay. So set seed of 1 will get us a certain result. So we're getting now our fit 1 in exactly that fashion as we had it before. It's reproducible and it will yield the same result. If we're setting the seed now to 10, we will get in the same fashion the second result. The second coefficient will considerably comparable, but it's a different coefficient, right? So if you compare the coef of fit 1 to coef of fit 2, this will be different coefficient. Right. We have here 2 different coefficients. With these changed, oh, this was two, fit 1A, fit 1A, fit 1B, fit 1B. This is the fit 1A, this is fit 1B. Okay. That should make sense now. So the difference is going to be considerably marginal because it's still somewhat comparable, but you see that there are differences in the reproduction, right? So this is what is meant in this lab example, that we understand to what extent this differs with different simulations. So this can easily be done, and you will then see in a larger scale how others change. So choose a different magnitude of confounding from the observed confounder sex, refit the model, and observe the change of the impact of SL to SPP. So now we have sex we haven't had included yet, but we go back to taking the fit. Yeah. We're going back to setting the seed. We're bringing that back down here. And now we want to change the effect of confounding by sex. So we have here, once again, we have set the seed at 1. We have age, sex, or simulated variables in the serum glucose here. I just want to again outline, so these examples are not reflective of what you would really observe in real life. So this definitely will not be a blood pressure value that we'll see in real life. So we're doing now a beta for beta sex equals, I don't know what the answer be showed, so let's say it must be 0.8. So we're replacing now this with beta 6. There we go. And this will give us a fit. We're gonna take from up here. So this is our fit 3. Oops. So this is the fit 3, 3A. 3A. Okay, fit 3A is now the effect of serum glucose plus age plus sex. So now 3A is going to show us a result that essentially incorporates all these 3 variables in the prediction. So we have now effects for serum glucose. So the interpretation is that 1.94 increase with each unit of serum glucose, 0.44 increase with each year of increase, with each year of age. And sex basically means, well, it depends how you are coding it. If you say male, for example, is 1, you would have a decrease of 0.8. No, actually, for females, female sex usually has a smaller value for blood glucose. So, so female would be 1, and with female sex, we basically have a smaller, all else being equal, we have a smaller systolic blood pressure of minus 0.18. So now, if we change the magnitude of this now, so we have in the first iteration we have 0.5. In the second iteration, let's do 0.8. And if we're looking at this now fit 3B, and you do fit 3B, it shows what we would expect, that our COF fits 3A and COF fits 3B. So now this fits 3A and fits 3B. So we see that the effect of sex here changes the slopes as well as the intercept. And this essentially is because of a change in simulation of sex, and thereby the entire model changes accordingly. So if there's a stronger confounding effect of sex, this has ramifications for all other slopes. So this is basically what is being meant to be shown here. So you basically, you refit the model and you observe the change of the impact of serum glucose. So you see effects on intercept, you see effects on serum glucose, age, barely on age. So actually a smaller effect on age, because that's how it's set up, right? And this comparison was actually that part of this investigation. So you basically see that the coefficient does affect all other covariates, or the estimates, the beta zero and the beta estimates. Try other changes you might consider. So magnitude of error for serum glucose and blood pressure. So we can do that by just copying this. Is this clear so far? Or I think it's quite easy to follow along, right? Programmatically, it's a little tougher. But do you have any questions, Shidhar, Adil?
So far, no. I'm just trying to follow along as much as I can.
Yeah, same here. I'm trying to follow along. I actually haven't started this lab yet. I was doing the 2 lectures first.
Okay. Okay.
Yeah, but we'll get the discussion board started if you do have any questions.
Yes, please, absolutely do. Absolutely do. Yeah, so essentially you're doing the same thing, but this time around, let's log beta6 in. And let's change here the variability, for example. Let's say there's a larger variability with age. There's a larger variability with serum glucose. Actually, let's change it to the second model. So you will see that these estimates will change to some extent. Since the means remain the same, they will not change as much, but what definitely will change is the precision of the estimates. So now this would be fit 4A. So it is really important. It's just important that you understand the different components that you're facing here. And this is really the beta6 is just replacing here, manually replacing this coefficient. If you change the standard deviations, you can, of course, also change them directly here. Actually, it's not good if you change both. Let's just change one. Let's change STV. STV, I think that's how they labeled it in the answer key. So STV here is 5. So this is then STV. So you're just using these objects and you're replacing these objects, and then you can change these estimates easily by just comparing the coefs. So you basically have beta6, 5, that's the same. So STV is now 8 rather than 5. Okay. So now we're changing here the STV, or else being equal. And you see now different estimates and variations around these estimates. So just to put this in perspective, so now we have coef fit 3A, now we have coef fit 4A with the changed standard deviation, and we have now coef fit 4B. That essentially shows now different estimates, as you can see, right? And this is explained by the variability. They are somewhat comparable, even if you changed the variability, but the strongest effects you see here on the intercept as a consequence of the slopes changing a bit, but the intercept will basically, because it's an extrapolation of your estimated function, will essentially change the most. So what you also see different will be the standard error, which you could export as well. But this is basically where you see the largest change then in the estimate and in the different models. So, and finally, write a for loop to gather results from 1,000 seeds and quantify the percent bias of estimating coefficients of SL due to omitting confounders. So, and this is now an interesting exercise, and we can now go to the answer key, which I've provided to you. So essentially, and I'm going to walk you through this now. So you're basically setting the seed to some arbitrary number, and you are basically aiming to reproduce the same model 1,000 times. So you're replicating next to each other. You're basically replicating the same, or should I say, the same data 1,000 times. So you get an R norm of 1,000 individuals. You're replicating 1,000 times. And then you're basically, no, that's actually not the right one. No, that's true. Oh, but I found it was a for loop. Okay, so you're replicating this 1,000 times, and you basically replicate, and then you're repeating this 1,000 times. So your outcome here, the one true not found, and this comes from the original one. Oh, that's cool. But this is your better true. Okay, and that's it right there. Okay, better one true. That's your true better, which we have used before. You remember this is when we used this better one true. That's predicting it now based on our true better. Okay, so now we do a repetition of 1,000. So this is basically just assigning a certain number to an object. So now you have better one C. A is now a vector with the same length of num reps. So this is 1,000 zeros, which essentially you will be replacing now with your for loop. So you create a my seed that is basically following along with the sequence of the length of these num reps. So if you take this sequence, you get 1 to 1,000, right? So you're going from my seed, and this is your I that I showed you before in the for loop, in the sequence and in a sequence from num reps, which is 1 to 1,000. So you set the seed every iteration. You're setting the seed that respective corresponding number from the 1 to 1,000. So you basically, with every iteration, you're reproducing them, or you're producing a new variable that you then use in your model. So if I do set seed at 1, if I say, okay, so let's do set seed equals 1, I do the same thing as I did before, right? So this is if I say, so tag it out. If I say my seed equals 1, I get now the first set seed, and I get these estimates with a certain kind of simulated data set. And this summary might fit is one that we've seen before already. And now with every different my seed, we're going to get a different model and a different estimate. Oops. We get a different estimate of our fit coefficients. So these will differ with every change in my seed as a numeric value. So now what you do here in beta1.ca, so this is the estimated, like the alterated kind of model output, and with coefficients of my fit. Coefficients of my fit is our model. With coefficients, you get that coefficient out, that is SL. So that would be in our case here 2.05. So you're grabbing this coefficient and you're adding it to beta1.ca, which is your vector of the length of 1,000. So if you're running this 1,000 times, your actual outcome, so this will take a little bit, because it's building this new simulated data set with each iteration, right? So if you're looking now at beta1.ca, you basically get a list of 1,000 entries, all different coefficients, with these reran iterations of that model with all a different coefficient. And so the idea here was then that you create the proportion of the bias. This is essentially then run iteratively. So R will always go through data sets in an iterative fashion. So it will go row-wise from the first entry down to the last entry. So beta.ca, we see here, that's the list of 1,000 numbers. Beta1 true is one value. So this is 2. So now, basically, R will create here the difference between beta1 CA, all these 1,000 entries, minus 2, our true beta1, divided by the beta1 true. So this is that proportion of bias introduced by this one variable due to the set seed change. So you get a proportional bias, and if you multiply this by 100, obviously you get then a percentage, and with a mean, you get a mean value of this proportion. So overall, the proportional bias for all these 1,000 entries is 2.14. And this is basically what was being asked for. So this is now the replicate. So you can also do this exercise with replicate, right? With replicate, we're creating, if we replicate this 1,000 times, we get entries 1,000 times over the exact same number vertically in a wide format. So you can do the same exercise that we did before. We're building with replicate, beta1 CB. And it's good in R to know different approaches to problems. And because sometimes those that are computationally less intensive will allow you to come to your answers faster. So now we have beta1 CB. And that's essentially now the same vector, but approached in a different fashion. So we're basically, what we're doing now is we have a beta1 true, but we're replicating 1,000 with different seeds, right? And now we're getting, again, the same approach, which we wanted to get for our mean. So we get, again, our 2151. Let's set this again, just like before. 14. No, actually, no, hold on. No, because the seed was the same. Oh, there's something off. No, there's a part missing. Hold on, but I need to look that up myself. Okay, but you've seen with the for loop, you've seen now how to do that. I will look into how to simulate this replicate. Okay, so back to the for loop. Let's focus on the for loop for now. So is this in principle clear what was meant with this for loop? You're changing the my seed. You're setting the seed on a vector from 1 to 1,000. You use different set seed values. You create different models. You run on these data sets, different models, get the different coefficients out. You get a beta1 CA, which is your simulated changed CA, and you're comparing it to the initial one, where your beta1 true was 2. And then you calculate the proportional bias. Does that make sense?
A little bit.
A little bit. Which aspect? Which aspect is not entirely?
I guess I just have to start from the beginning again. I keep messing up on. Yeah, it's not that it's not clear. It's just I haven't, you know, done it properly.
Yeah. So
And
have you used a for loop in other languages, like in SAS, for example? Did you use iterative loops in SAS?
no, we haven't used for loop in SAS. The only programming language I know is like basic SQL, and that's really about it. Yeah.
Well, you do have iterative loops in SQL, right? So iterative loops in principle, I just want to repeat then the for loop part of it. And this is because that's really the basis. That's the take home message, whether you use for or replicate. In this context, I find to replicate a little bit hard to start with as well. But if you go for the for loop, and this is really what's most central at this point, to understand the for loop in its principle. And the principle is really you have for, you have one placeholder that iteratively changes with each loop. And after the in, you're defining what will this iterative variable, this kind of local variable within the for loop change to. So you go from 1 to 3, and it will take each value on that sequence that you presented. So if you say 1, 2, and 3, it will run it 1, 2, 3, or it will run it 1 to 1,000. And then you can utilize this change to basically change the seed. And this was done with the seed example, right? So you have here for I, 1, and 3, you're printing I, and you see exactly you print 1, 2, and 3. This is the basis of the for loop. And if you do this now with set seed, not the replicate. Don't focus on the replicate for now. Focus on for example. Focus on the for example. So you have for my seed. My seed here essentially is just a variable. This is the I. And you have a sequence of num reps. And this num rep sequence is 1 to 1,000. And you assign here 1,000 as the number of 1 reps. And if you say a sequence of any variable, of any value, will essentially be nothing else but a vector of 1,000. So it runs it from 1 to 1,000. And it runs it 1,000 times. It runs it every time there's a value, iteratively going one entry to the next. And then you basically, what you're doing here with set seed, you're grabbing each respective my seed value, and you rebuild your simulated data here. And this simulated data is essentially used then to build here your model. You build a summary of the model, which you don't even need to do. So that's a superfluous entry. And actually, in the for loop, it's never going to be shown. There's no point. But then you assign to better one CA, which you defined up here as a vector, a numeric vector, from 1 to 1,000. So you have here 1,000 zeros. And these 1,000 zeros, essentially, you then replace with the coefficients of each iterative MyFit model. So you're building here 1,000 models. You grab the respective coefficient for SL, for serum glucose, and you're replacing that respective entry in your better1.ca. That's make it a little clearer. And then essentially you use the same iterative approach in R to basically one by one, you go and subtract the true beta, which is 2, from that faux beta with the different seeds, and you divide it by the true beta. That gives you a bias, that gives you a change with each seed. And this bias you quantify by multiplying it by 100, and you get a mean of all these 1,000 bias estimates. And then you get a mean bias, which is essentially, now it's minus 100 because we're subtracting now a certain value that doesn't make any sense. But if you rerun the whole thing, it basically builds the mean of this difference divided by the true value. just re-watch the recording probably and try to play around with it. If you have questions, we can discuss it again on Wednesday if you want.
Sure, yeah.
Professor, you had a great example of the glomerular filtration rate, the GFR, and normalization. I just wanted clarification, like, is the GFR both normalized and standardized? How exactly do they do that?
Help me a little further. That was from the lecture.
Yeah, so class 3, it was the 4th slide. It says normalization, standardization, and centralization.
3, slide 4, yeah. That's not glomerular filtration rate, I believe that's yeah, with the glomerular filtration rate, that's a little bit different. So normalization is essentially where you rescale something to a response variable, right? So you can so you normalize something. I know what you mean, what I said in the lecture. Yeah, so this is the normalization to body weight and body surface area, right? So you can normalize things to whatever you deem important in the context of normalization. So the glomerular filtration rate would be normalized to a body parameter of that individual you want to use it for. So you have an individual that has a certain glomerular filtration rate, but you know that somebody who has a larger surface area is essentially having a larger glomerular filtration rate. This is why it's being normalized to one particular surface area that is being used. So this is in medicine over the years, it has standardized to 1.73 square meters of body surface area. So this being said, you can use it to all kinds of different response variables. So Professor Seng talks here about logarithm, square root. So essentially, you normalize it in this context to normalize it to a population, right? And centralization is essentially then referring it to shifting a covariate by subtracting the mean from the original value. So you basically you centralize it to the population distribution. Whereas this normalization I was referring to with the glomerular filtration rate is normalizing to an individual in order to centralize it and make it comparable amongst people of different surface areas. So it is not the normalization that Professor Sang. So he talked about a normalization in a way to make it more comparable to normal distribution. So you rescale a continuous response variable that is not normally distributed by logarithm transform it or by square root transformation to basically have it to meet the normality assumptions. The normalization I was referring to is a physiological normalization that allows you to compare amongst the population between individuals in that population. So, but yeah, the normalization that is referred to here on slide 4. So this is to make the response variable more normally distributed, or allow for it to include it in regression model that have a normality assumption. And standardization is essentially you referring to a standard distribution. And this is the calculation of the set scores. You remember this from page 614, where you standardize an entry of an individual amongst a population and amongst the distribution of the population from a mean and the standard deviation. You standardize each individual based on the population distribution. And therefore, you can make individuals also comparable in some shape or form.
Yeah, that was very helpful, Professor. Thank you. And
yeah, does that answer your question? Okay. So the glomerular filtration rate. So I keep on going off in my personal research areas. So that was probably in the context not what Professor Sang meant. So this is really more of a specific example. But I'm glad it was helpful to some extent.
Yes, no, that was helpful, Professor. Also, are there practice problems you would recommend we do for the theoretical part just to reinforce it?
Well, go along with what you learn in the labs and understand the examples that you learn in the labs. So the labs will basically accompany the lecture, and the examples are kind of tailored for the lecture and the topics discussed in the lecture. So I think these are basically solid programs. As for the rest, so Open Intro is, I have included this in the syllabus, right? Open Intro is a very useful book that essentially also allows for practice examples. I can post some additional examples or some specific examples from the book if that is helpful.
Yeah, I'll look at Open Intro again. I really like that text.
Yeah, it's a very good book. It's a very good book.
All right.
Okay.
Those are all the questions I had. Thank you so much, Professor.
Okay, great. You're welcome. Any other questions from you, Adil?
No, I'm good as well. I'll look at this recording when you post it again, and then if I have any more questions, I'll definitely post it on the discussion board before
Okay,
the labs do.
Yes, that's a good idea. Yeah, please utilize the discussion board. I'm going to be back on Wednesday, and we can discuss further Lab 4, or we can go back to some conversations we're doing here, some of the topics we discussed today.
Thank you.
All right, sounds good. All right.
Thank you.
Thank you, and have a nice evening.